Hello, my name is Michael, and this is our CS225 final project. We built a graph representation of airports and routes for this project. Before moving on, I would like to let my teammates introduce themselves.
Hi, my name is Elijah. I'm a sophomore in computer engineering at UIUC.
Hi, my name is Boy.
So our goal for this project is to help people who need to travel by air to find the shortest path between the source airport and destination airport. The idea is that we represent airports and route data as a directed graph, which uses airports as vertex and routes as edges, and run traversal and other algorithms on it. We did several things to achieve this goal. We built the depth-first traversal, which is used to return all airports that can be reached from the source airport. It takes OV plus E time. Next, we use Dijkstra algorithm to find the shortest path between two airports. Finally, we successfully built strongly connected components algorithm. This algorithm is used to determine whether two airports can reach each other. All algorithms, which are DFS, Dijkstra, and strongly connected components, are built and run in appropriate runtime constraints.
So in data processing, which is the beginning phase of this project, after we acquired our data from OpenFlight, we need to perform data parsing to get only the 3-letter code and the coordinates. It's quite a challenge with C++ since the data set is not fully accurate, so we need to perform data correction as well. Another challenge we face is accessing time for the airport vertex. Since airports have 3-letter IATA code, we store them in a hash table, which is on the map. That the key is IATA code and the value is airport vertex. Each airport vertex contains IATA code and their coordinates. Next slide. So in graph construction, we need to figure out which way we can represent our graph. During class, we talked about that typically there are 3 ways: edge list, adjacency matrix, and adjacency list. Each method has its own pros and cons. We found that our algorithms run better with adjacency lists since it takes less running time to get incident edges and to insert vertex. In the beginning, we use pointers for everything. It runs somewhat right, but when we try to run algorithms on it, it generates a lot of troubles for us. Even though pointers take much less space and is faster, there's a lot more bugs that come along with it. Since the full data set is not that big, we end up using strings as keys instead of pointers. Next slide.
For the depth-first search algorithm, our goal is to traverse the whole graph, beginning with the designated starting airport, and expect an output of a vector of string, which contains all the airports that current airport can reach. We firstly refer to the MP traversal to write the DFS as a class, but we eventually were stuck at the iterator part of that DFS class, as the pointer-induced bugs make us pretty confused. However, for the project, it is actually not necessary to adopt DFS as a class with its pointers or iterators, as what we have in the MP. We finally decided to use traversal as a member function and traverse all the string vertex successfully. During the development of Dijkstra algorithm, the implementation of it is pretty smooth for our project. However, at first, we were trying to create a Dijkstra class outside our graph class. In that case, some linking errors happened unexpectedly during the combination. So eventually, we turned the Dijkstra into a member function of the graph class, which prevents any combination error happening. For strongly connected components algorithm, we originally intended to adopt Kosoraju's algorithm, which is really efficient. However, due to a lack of knowledge of topological sorting algorithm, we decided to alter to our current algorithm. Our current algorithm basically contains two steps. Firstly, run DFS twice on both the original graph and the transposed graph. Then we find the union of the two generated set of strings, which are the airports as a strongly connected component. We have two main implementations for strongly connected component. First one is to find a strongly connected component that contains a certain specific airport as an input. And the second one is to find all the strongly connected components in the graph. As a result, we decided to use passing by reference rather than passing by value for DFS, as both implementations need to run DFS multiple times. In that case, we are able to save running time from 10 minutes to 10 seconds.
So we wrote test cases that use simple data set that we created. In these data sets, we use actual IATA codes and their coordinates, but we routed them very differently. The reason why we use actual IATA codes and coordinates is that we can also use this simple data set to test our Dijkstra's algorithm. Here are some graph representations of our own data set. This one we use to test DFS and Dijkstra. Next slide. The left one is used to test Dijkstra as well, and the last one is used to test our strongly connected component algorithm. These sample test data set are useful since they are small and effective. They can help us to locate our problem very quickly since we build them, so we know what the ideal solution should be. Next slide.
In conclusion, we built 3 algorithms to achieve our goal. The DFS outputs a vector of string, which contains all the airports that current airport can reach. One thing we find interesting here is that when we run the traversal for specific well-known airports like O'Hare, almost all airports over the world can be reached from it, which forms a huge connected network of airports. And the second algorithm, the Dijkstra, outputs a vector of string, which represents the shortest path between 2 airports. The path only optimizes in distance, but not in time. The third one, the strongly connected component, has 2 functions. Like we said before, one function returns SCCs of the whole graph, and the other one returns the SCC that the specific airport that is in. One thing we find is that DFS can be used to find the strongly connected component as well. What makes them different is that by using SCC, we could run through all airports and find its strongly connected components, whereas the DFS can only run through the airports it can reach.
Okay, so I have some final thoughts, but one of the most interesting part is when I see what Dijkstra returns to us. It will return the shortest path, but most of the time, we might not want the shortest path in return, because the shortest path, it's not shortest in the way when we choose the path to travel, because most of the time we don't want shortest in distance, but we want the shortest in time. So if we have more time, I would try to implement constraints on time. Yes.
For the strongly connected components, I'm also interested about what is the real world implementations for that. If we have a look at our output of our strongly connected component algorithm, we can check the size of it. In that case, we can know how many airports are there in the mostly strongly connected airports maps. And we are able to identify whether or not a specific airport is in this strongly connected component. Also, we can check any airport during this component can travel to any other airport in this component. Secondly, we can also identify and analyze the area where airports are relatively isolated by checking the size of the small output of the strongly connected component. That means that the output of it has smaller elements in it.
And one thing I would like to mention is about the Dijkstra algorithm. The path returned by this algorithm we built here is the shortest in distance. However, when it comes to the real world application, the distance is now the only decisive factor in how people choose their flights. What I would like to explore next is to implement new functionality that returns the path which contains the smallest number of airports in it. To achieve this goal, the breadth-first search algorithm can be used, and the old code might need to be refactored so as to maintain its features we already built up here. And that's the end of our presentation. Thank you.
Thank you.
Thank you.